Calculus!
This is AP Calculus Lesson 10-1. You guys have the unit guide in front of you. You'll notice that there are only 3 lessons for this entire unit. It is very, very short. I'm going to turn off all lights. I wonder how that registers on this microphone. I haven't yelled at this microphone for a while. So, general fundamental theorem of calculus application. So, fundamental theorem of calculus, again, that is start plus change equals end. That is where I need to find that constant of integration. That is taking the inverse of a derivative. So, I take the antiderivative of the derivative, and don't forget to do that start value. Okay, so specific versus general functions. And this is going to be some letter. So I'm just going to choose, let's do W. So if I have a function W and I take its derivative, what do I get? Let's take the derivative with respect to t, with respect to time. The derivative would be what?
W.
No.
W prime.
W prime, but you need to be very specific now because W prime assumes we already know what we're taking the derivative with respect to, but now I'm saying you need to say you're taking the derivative with respect to time, not with respect to x, not with respect to y, but with respect to time. How do I say that?
Just d over dt.
dw dt. You remember how to write these derivatives? Yes? And if I take the derivative again, what do I have? This one you might not have seen. It's a little bit tricky.
D squared w over d squared t.
Okay, you're so close. I'm going to write the top because you got the top right. The numerator. D.
Oh, is it dt squared?
Yeah, it is dt squared. D squared w over dt squared. It is weird. And there is an explanation for it. I still don't have my head fully wrapped around the reason that this is. I've seen the formula and I'm like, okay, I nod my head, that makes sense. For now, let's just assume that this makes sense to us and just put the square root over different things. You're taking the derivative again, so the top is saying I'm taking the derivative again. I'm still going to have another dt, so this whole dt squared, I have 2 of them. But taking the derivative of w, you have to say I'm taking the derivative twice. That's generally why you have a d squared on the top. All right, let's talk about position. So if I have a position function, we're doing position, velocity, acceleration. Position is given by usually what? What letter do we usually use with position? X, Y. If you're going up and down, it's usually Y, X. If you're going left and right, let's do X. X of t. If I take the derivative of X of t, what do I get? If I take the derivative of position,
dx dt.
You're right, dx dt. What is the derivative of position in terms of just the concept? What letter do we choose now that we've taken position? Derivative of position is
V.
V, yes. Velocity of t. And when I take the derivative yet again,
Oh, it would be a of t.
a of t. Yep. No barking yet, but let's see here. All right, so generally speaking, you will have, when you're talking about a specific function, you'll have a value. And then once I take the derivative of that value, then I get the rate of that value. And then when I take the derivative again, I get the rate of the rate, right? So let's say that. Let's say if I start here, if I have a value, and I take the derivative, then I'm talking about the rate of the value. And when I take the derivative again, it's usually the rate of the rate. I'll just say rate of the rate. Rate of the rate. All right. So general functions are not like specific functions. Specific functions are analogous to taking the definite integral where we have bounds on our integral, and general function is analogous to not having bounds. We all remember having bounds on integrals? Yes, yes. All right, so if I have f of x, we'll just say f of x, some general function that we don't know. If I take the derivative of f of x, the most simple way of saying that using the prime notation would be f prime of x. And taking the derivative yet again, how many primes do you have, Arrow? Yeah, 2. F double prime of x. All right, so say I have, now let's start with y. Let's say instead of f of x, let's call it y. And now I want to use this top notation, made popular by Leibniz, this top notation with y, and I'm going to take the derivative with respect to x. How am I going to write that?
dy over dx.
Yep, dy dx. And if I take the derivative again, it's basically the same as this guy, which is what, Rochelle? Undo. See, this is why I need an undo button. Also, I've
We
learned
use a different PDF program.
this PDF. I searched so long for this PDF program now. D squared y over dx squared. You can write smoothly on a PDF. If you can find another Mac application that allows you to write smoothly on a PDF, let me know.
So that's the problem.
Yeah, there's Adobe Acrobat, but what it does is it makes all the writing, it tries to curve everything to smooth it, yeah. And it's just horrible. I've tried a few other ones and they're glitchy. This one has glitches, but it's something that I can deal with. But these two are the same. Like if you have a value, you're talking about the rate of the value, the rate of the rate. It's still a general function, but I'm not saying anything new. This is all review. If you have a value here, then it's going to be the rate of the value, and then the rate of the rate.
What's the difference between specific functions and general functions
What
and
a-
functions with values?
What a great question, yes. Can you ask the question again?
What's the difference between specific and general functions with values?
So general functions, we don't know the bounds. So you remember how fundamental theorem of calculus, you take the integral of a rate. We all remember that. Take the integral of a rate, so you take like the integral of f prime or something like that. So the specific function will be the integral from 1 to 2 of a rate. The general function will be like the integral from 0 to a of a rate. So we'll have more variables. It'll be a general answer. And the answer can be answered with, a variable. My shoelace is untied. All right. So let's go through a few examples so you can see the difference. This is answering Rochelle's answer, or question. There we go. So I know it's usually start plus end equals, start plus change equals end. I'm going to do end is equal to start plus change, just because the end value is the one that we want to see how that varies. That's going to be our starting value. So the end, I want to put here, end, and I think I'm going to do start plus change. Yep. End is equal to start plus change, All right, if my end value is, I don't know, let's talk about that original w function I had, w of 20. So every single time that you start at whatever it tells you, your initial condition. So in the problem, it'll say, assume that you start at time equals 0. So I'm just going to say w of 0 in this case. Usually, if they say time equals 0, you could say w of 0. That would be one example of a starting value. And these don't correspond to any specific problem. I'm just giving you examples of what you might encounter for a start problem. That means if I'm doing an integral, what is my integral going to be? And this is really where the fundamental theorem of calculus varies between general and specific applications. I have my bounds now. What are my bounds?
0 and 20.
0 and 20. 0 to 20 of what? W prime, exactly. So I can either write W prime or I could say dW dt. In this case, I'm just going to randomly say dW dt. But saying W prime is 100% correct. So I'm going to say dW dt. Exactly. And then I guess if we're being technical, we still need to multiply by thickness dt. All right. I'll give you another example of a specific. I'm going to make these first 3 specific, and I'll make the last 2 general. So let's talk about the position. So if I'm trying to find the total position change, that means I'm trying to find like x of something. Let's do x of 5. I want to find where am I at time equals 5. Let's go ahead and assume that we're starting at time equals 0. So I'm going to say my start value is going to be x of 0. Non-Ben, someone aside from Ben. What are my bounds?
0 to 5.
0 to 5. So my change plus is going to be an integral from 0 to 5. Of what? And try to use the notation that we just used up above.
Should be dx over dy dt.
So you're right in thinking it's the derivative. But if I'm talking about position and x represents position, what is the letter that represents the derivative, the change over here? Because it's always the integral of a rate. You're always going forwards, taking the derivative, and backwards, taking the integral. So the rate of position is also known as what letter?
R.
We just wrote it down up above. v, yes. So the integral of v of t dt. There we go. Whenever I'm doing fundamental theorem of calculus, I'm always going to be taking the integral of a rate. Integral of a rate, over and over again. Sometimes it'll be in this form, sometimes in this form, or sometimes in this third form where I'm going to do a prime.
How do you know what to use instead of bt, a of t?
Oh, when do I do a of t? That's when I take the derivative again. If, for example, I wanted to find the velocity at 5, then I have to do the initial condition velocity of 0. Then I have to go up to the next derivative of velocity, which would be a. Let's actually do that one. That one is a good one. So let's say I want to find velocity of some function, velocity of 3. Let's say that we're still starting at time equals 0, so nothing new in this column. Still the velocity at 0. And then someone regurgitate to me what I just said. 0 to 3 of a of t dt. Yep. You always go up a derivative when you're using the fundamental theorem of calculus. So far, so good? Okay. So far, this is all review. You've done this before. Now is the slightly new stuff when we're talking about taking the general form. Okay, so let's say I'm trying to find some value. So I'm going to say my function is f, and I want to find the value when I plug in b. Notice it's no longer a number. And let's assume that I start at some other number. I'm going to call it a. Let's assume I start at a. So I'm going to put f of a for my start. So using the prime notation, so if I'm taking the derivative, it's prime. Taking the second derivative, it's prime prime. What should I be writing here for the change?
Integral of a to b.
Integral from a to b of f prime, careful. X, yep. Whatever you normally put in there. Maybe it was the normal function was with respect to x. Maybe it was with respect to a different variable. But there it is. Maybe you could have said t. Usually it's x or t for AP calculus, and then dx dt, whatever it matches. Let's just try it again. This is a different scenario. So if I have g of b, and I'll start at 0. Let's say that we actually have an initial condition, so it becomes g of 0. This is still general because we still have one variable. So this one is going to be what? Using prime notation again. Integral of what?
Integral of
0 to b. Of? There it is, g prime of x dx. And you could say x, it could be t, it could be whatever you want. I'll do x again, g prime of x dx. But I mean, it's pretty straightforward. I don't need to spend that much time. You always have two things you need to remember. General has letters, specific has numbers. Whenever I'm doing start plus change, the start is going to be the original thing that I'm looking for, g and g. And then when I'm trying to do change, I do the integral of the rate, integral of the derivative of whatever I'm finding. That's it. Good? Thumbs up? Yeah? Cool. That's it. That is the end of the lesson. Go ahead and write your summaries.